Hello friends, the topic for today is 8087 80387 instruction set, arithmetic and other instructions. In the last video on instruction set, we have discussed the data types, data registers and data transfer instructions of 8087 80387. In today's video, we'll discuss the arithmetic instructions in details and other instructions comparison, constant, transcendental and processor control. In brief, let us start. Welcome to our channel Engineering and Technology for You. If you are not subscribed, kindly subscribe the channel and press the bell icon. The topic for today is 8087 80387 instruction set, arithmetic and other instructions. We'll directly start with the arithmetic instruction. Arithmetic instructions. We have instructions for addition, subtraction, multiplication, division and other operations. In addition, we have three instructions: FADD A, FADD, FADDP and FIAdd. That is for say the addition of floating point numbers, then addition of floating point number with pop, and integer addition. Similarly, for subtraction, we have F sub P and Fi sub. Now this here I is for the integer, and if there is no alphabet, then that means it is for the floating point. And we have here reverse subtraction, that is source divided by source minus destination. So we have these instructions, three instructions for that. In multiplication, we have the three instructions similar to addition. Then for division, we have again 6 instructions similar to subtraction. And for other operations, we have the square root, scale, then partial remainder, round to integer, absolute value, change sign, these instructions. Let us see the basic instruction forms. We have 5 basic instruction forms that may be used across all 6 operations. So here the first form is the classical stack. So in this form, the 80387 works as a classical stack machine. So when it is working as classical stack machine, it will perform the operations on the stack. So the operands, it will pick up the source operand and from the stack top, and the destination operand will be one of the registers. So this is the source and this is the destination. So here we have taken by default these will be the operands, stack top and the next element on the stack, that will be another operand. So when we are performing the addition, so here is the example FADD. So these two operands are added and the result will be stored in the destination. So here you can see, here we have given the nodes. So these braces, they indicate the implicit operands for the instruction, and they are not coded here, they are shown for information. So and the operation add, so it will add the destination plus source and the result will be in the destination. So here st1 is the destination, st is the source, st is the stack top and st1 is the first next element in the stack or the stack register. So the classical stack, it will pop the elements and perform the addition, and the result will be stored in this destination st1. Then classical stack extra pop. the operation will be similar to this one, only after the operation, the extra pop operation will be done for the stack. Then in register form, we have, it is generalized form of the classical stack. The programmer specifies the stack here STI, so it can specify the particular register of the stack, and the stack top, that is the source operand. Destination operand is ST with any register we can take, say 2, 3, 4, 5, 6, 7, like that. That is the say register operand here we are, and this is with register with pop. So again, after the operation, the pop operation will be performed. Then the last two, real memory and integer memory. Here we are involving the memory as one of the operand. So that will be the source operand, and the stack top will be the destination operand. So here we can take the single or double precision, the real memory, or word or short integer memory. So in this way, these are the 5 instruction forms which will be common to all the, say, these are the 6 operations, whatever are there will be common to all these operations. So we have these operations, say add, sub, then this is reverse subtraction. So here the source minus destination. In sub we have destination minus source, only here the operands are changing. Then multiplication, destination multiplied by source. For division it will be destination divided by source, whereas the reverse division, it will be source divided by destination. So this is what this, if you remember these basic things, you can know all the instructions, you can understand all the instructions. Let us see the addition instructions now. So we have 3 instructions: FADD, FADDP and FIADD. So these are for the addition of real, real and pop. So this is FADDP, means to perform the real addition and pop. Then FIADD, that is for the integer addition. So again here what the common thing, the source and destination operands are added and return the sum to the destination. So that will be the common thing. So depending on, so let us see the FADD and FADDP instruction in details. So it will take the different forms as we have discussed the classical stack, register and so on. So FADD, so here there is, we are not given any operands, so it will take the implicit operands. So ST1 will be the destination, and the stack top ST0, that will be the source operand. So they are added and the result is stored in ST1. Then FADDP, that is again the same operation will take place, only after that it will pop the stack, pop 2 values on the stack, add them and push their sum back to the stack. So same operation as FADD, only additional pop operation will be taking place here. Then these are the other forms, that is the register form. Here we are specifying the registers. So if you take this, now this is the source, this is the destination. So STI, so here I can vary from 0 to say 7. So if you take this, the STI plus ST0, that is the top of the stack, that they are added, and the result is stored in the destination register. So if you take I as 3, then it will be ST3, that is the destination. So ST3 is added with the source, that is the top of the stack, and the result is stored in ST3, like that. And similarly, here we have taken the destination as ST0 and STI is the source. Then if you take the FADDP, in that case the addition will take place and the result is stored in STI, then pop. So after the operation, the pop operation will be performed. Then with memory, we'll add the stack top ST0 with the memory, which may be 32 or 64 bit, and the result will be stored in the stack top, on the stack top, not in memory. Then the normal subtraction, we have the F sub P and Fi sub. So these three instructions, so they are for the subtract real, then subtract real and pop, and integer subtract, these three operations. So again, the source operand is subtracted from the destination and the result will be in the destination. So if you take the example F sub STI ST0, so this is the stack top and STI is any other register on the say from the data registers. With here we have taken the index I, so I will be from 0 to 7. So the destination minus source and the result is stored in the destination STI. So if you take particular example, here we have taken F sub ST3 and ST0. So ST3 minus ST0 and the result is stored in ST3. So this is nothing but the element on the stack data registers, that will be depending on the value of the, so always this ST0 will represent the stack top and this is another register from the data register. So in this way we can understand the instructions. Then reverse subtraction, here again we have three instructions, F sub R, F sub RP and F sub reverse Fi sub, that is for the integer subtraction. Again the things will be similar, that is subtract real, but here only it is reversed. Then subtract real, reverse and pop, that is the second one, and last is integer subtract reverse. So if you take example, we'll take one example here, F sub R st comma st1. So here this is the source and this is destination. So subtract st from st1. So from source we are subtracting the destination and the result in here will remain st, this is the destination. Then multiplication. In multiplication again we have the same three instructions, that is multiply real and pop, and integer multiply. So these are the three instructions, fmul p and fi mul. So again multiply source and destination operands and return the product to the destination. So this is the similar operations like addition, it will take place. Now here if you take example, now here we have given fmul st comma st0. So st is nothing but the stack top and st0 is again the stack top. So it will square the contents of the stack top, and it will be result is stored in the stack top only. It will be present there only. So in this way we can use the different instructions. Then normal division. So normal division, again we have three instructions: FDIV, FDIVP, and FDIV, FIDIV. That is for the integer divide. So here divide the destination by the source and return the quotient to the destination. If you take example FDIV ST0, ST5. Now ST0 is the stack top, and ST5 is another register. So here ST0 destination divided by the source ST5, and the result will be stored in the destination ST0, that is on the stack top. So we can take various examples depending on by changing the registers here. Then next is reverse division. Now here only thing is it is reverse. So divide the source operand by the destination and return the quotient to the destination. So if you take this example, here the source operand is stack top ST0 and destination is ST4. So source is divided by destination and the result is stored in the destination ST4. Then other things will be similar. Then F SQRT and F scale, these two instructions we'll see. F square root, that is replaces the content of the top stack element with its square root. So if you just give F SQRT, the stack top ST is replaced by the square root. Then F scale. Now F scale interprets the value contained in the ST1, that is the stack element 1, as an integer and add this value to the exponent of the number in ST. So here ST multiplied by 2 raised to ST1. So here we are actually getting the ST is multiplied by powers of 2. So it will provide the rapid multiplication or division by integral powers of 2. So it's useful in scaling of the elements of a vector. Then FABS and FCHS. Now FABS, that is the absolute value. So changes the top stack element to its absolute value. So just by making its sign positive. So whatever the MSB, the sign, it will be removed, cleared, and it will be positive. Then FCHS, that is the change of sign. So it will complement the sign of the against stack top. So this is for complementing the sign. So whatever is the sign, we can it will be reversed. If it is positive, it will be negative. If it is negative, it will become positive. Then let us move on to the comparison instructions. Now here, this class of instructions, that is for comparison of numbers of all supported, that is real and integer data types. Each of these instructions analyzes top stack element, often in relation to another operand, and reports the result as a condition code in the status word. In the previous video, we have discussed the status words. In that, we have the conditional codes. So C0, C1, C2, and C3. So here, that will be used here. So the basic operations are compare, test, that is compare with 0, and examine. These three operations. That is, we'll be discussing this. Then special forms of comparison operations are provided to optimize the algorithm by allowing direct comparison with binary integers and real numbers in memory. So that is also possible, as well as popping the stack after comparison. So we can take out the say, stack and store it in memory after comparison. So these are the instructions f com p. There is compare real and pop, and then compare real and twice pop. Double p means twice pop. Then fi com, that is integer compare. Then integer compare with pop. Then test. Then unordered compare. These three are for the unordered compare. And exam, that is examine. So we'll go into the details of this. First is fcom. So this fcom or compare real. So here there is no other alphabet, so it is for the floating point or real numbers. Compare the stack top to the source operand. So here we'll have to give the source. The source operand, now we can give the register on the stack or a single or double real memory operand. That is 32 bit or 64 bit. If the operand is not coded, ST is compared with ST1. So these are the implicit operands. The ST means stack top and ST1 is the next element on the stack. So after the after the instruction execution, the condition code reflects the order of the operands. So here if you can see C3, C2, C0. This is the CF, this is the parity flag, and this is the 0 flag. So ST is greater than operand, then in that case no flag will be set, all flags are 0. So that corresponding we have the JA, that is jump above, and ST is less than operand, then in that case the carry flag will be set, and that is we have the jump below. Then ST is equal to operand, then this 0 flag will be set, because after comparison the result is going to be 0. So here we have the instruction JE, jump on equal, and if all the flags are set, then it is the jump on parity. So in this way the compare instruction fcom will be used. Now if either operand is NaN, that is nothing but not a number. NaN means not a number. So either quite or signaling or an undefined format, or if stack fault occurs, then invalid operation exception is raised and the condition bits are set to unordered. So that is what is the meaning of unordered. Then let us go to the next fcom p. So that is fcom p, compare real and pop. So it is similar to fcom, only addition pop of the stack will occur. Then here fcom double p, please compare real and pop twice. So it is similar to fcom, and additional pops of the stack twice, discarding both the operands. So it will compare ST to ST1, and no operands may be explicitly specified. If we are not specifying, it will compare ST and ST1. They are the implicit operands. Only here additional pop is there. Then FICOM, there is for the integer compare. So convert the source operand, which may reference to word or short binary integer. So here the operands are integer, word or short binary integer, 16 bit or 32 bit. Then FICOM here integer compare and pop. When we add p, that means additional pop operation will be there. So it is similar to FICOM, only value in the stack top is discarded. by popping the stack. Then FTST. Now this is the test instruction, FTST. So test the stack top element by comparing it to 0. So it is compared with the 0. And here, if it is greater than 0, then again no, these flags are not set. Again it corresponds to J. And if it is less than 0, then the carry flag, 0 flag is, sorry, it should be carry flag. Carry flag should be set. It is corresponding to JB. Then ST0, again here this flag will be, 0 flag is set, so it will be jump on equal, and on order it will have the JP 111. So it is similar to the last table. Then FXAM, that is examine. So here it will report the content of the top of the stack element as positive, negative, or not a number, denormal, normal, 0, infinity, unsupported. So these are the bits and these value at the top. So this is not a number. It is, if it is unsupported, plus, minus, like that, it will give the conditions depending on these 4 bits. So this instruction is for examine. It will report the content of the top of the stack. Then constant instructions. So we have these instructions, FLDZ. So loads 0.0, that is 0 onto the stack. Then FLDI, load 1, it will load 1.0 onto the stack. Then FLD pi, that is it will load the pi. So that is pi is nothing but 3.14 value that will be loaded onto the stack. Then FLD L2T, so it will load a log 10 to the base 2. Then FLD L2E, it will load log of E to the base 2. Then FLD LG2, it will load log of 2 to the base 10. And FLD NL2, it will load log to the base E, log of 2 to the base E. So in this way, these instructions, therefore the constant, loading of the constant. Then transcendental instructions. Here we have the F sign, that is for the sign. So the stack top will be equal to sign of the stack top, that will be in radians. Then F cos, it will give the again the sign in terms of cos it will give. Then F sin cos, it will give ST0 cos of ST, and ST1 will be sin of ST. Then FP tan, that will give us y is equal to tan of ST, that is the stack top. So ST0 will be 1, the stack top will be 1 after the operation, and ST1 will have the tan of ST. Then FP A tan, that is arc tan. So arc tangent of ST1 divided by ST, so that operation will take place. Then F2 XM1, so it will calculate y is equal to 2 raised to x minus 1. So ST will be 2 raised to ST0 minus 1, and the values of ST will be from minus 1 to 1. Then FLY FYL2X, so here we'll have the log 2 to the base 2, the log of x to the base 2. So that will be calculated and it will be stored in the stack top. and last one log 2 x plus 1. This expression will be calculated and it will be stored in the stack top. So these are for the transcendental instructions. Then the last is process control instructions. Here we have the instructions for say FNIT, that is initialize processor. Then FLDCW, that is load control word. Then this is for store control word. Then store status word. Then this is for store status word to AX. So the status word will be stored in the AX register. Then similarly we have this for the clearing the exceptions. Then FSTENV, that is for the store environment, then load environment. Then this is FSave is for the saving the state, then restoring the state, FRSTOR. Then FINCSTP, that is increment stack pointer, INCSTP. So decrement stack pointer, DECSTP. Then free register, when you want to free the register, we'll use the FRE. Then FNOP, that is the no operation, and FWAIT is the CPU wait. So these are some of the processor control instruction in short. Now with this we come to the end of this video. If you have any questions, contact me on Facebook, Twitter, Instagram or Gmail. And if you like the video, press the like button, share with your friends and subscribe to our channel Engineering and Technology for You, and press the bell icon if you want to get notifications about the future video. And thanks for watching. Have a nice day.